Now it's time for the Nonimaging Optics Design Competition for 2026. And the question that we are asking is, can you fit the light from a square peg through a round hole? But before we go into details, I want to take a step back and go back in time 20 years to 1995. Because this is not the first time that we have run a design competition at this conference. As Tom said in the introduction, there was a competition back in 1995. I was unfortunately not present at the time. I was in kindergarten, so I could not attend. But I have looked at the proceedings and talked to the people involved, and I find the story kind of interesting. Because at the 1995 conference, Roland Winston presented this design challenge. And it's a bit long, so I'm not going to read it all, but I highlighted some important words here. So the goal was to take a spherical Lambertian source and design an axially symmetric projector that projects this to a 5-degree half-angle emergent cone. So I summarized it here with this sketch. And this sounds like a relatively simple challenge in a way, right? It's not very complex, and it's designed, the sizes are chosen so that the attendue is matched. So it should be possible, right? Well, turns out it's not possible. And this led to some interesting developments. So if we go forward to 1997, then that was the next conference. And at this conference, there were several interesting papers presented. The first one was presented by Rees, Schatz, Sports, and Spurkel. And here they introduced the concept of a skewness distribution diagram. So at the time, it was well known that attendue is conserved and that skewness is conserved in a rotational symmetric optical system. But the idea of bringing them together like this in a diagram was new. And with this diagram, you can easily show that it's not possible to solve this design challenge, not with 100%, because you will have a mismatch between the skewness distribution of the source and the target. So in this first paper, they derive a maximum efficiency, and they actually design a system to reach this efficiency. And then in another paper, Bortz, Schatz, Rees, and also Roland Winston extended this idea to inhomogeneous sources and targets. And not only that, but they presented a third paper where they show that if we relax the requirements a little bit and say that our optics does not need to be rotationally symmetric, then it's possible to go beyond these limitations of skewness distribution and achieve higher efficiency. So I find this kind of fascinating that like posing a simple challenge can lead to completely new ways of seeing something in the field. And after that, I will go forward again 20 years to 2025 because we ran a design competition this year. The challenge was to illuminate a Nonimaginum rod and find our way back home. Because the story was that this is in the future. You are exploring different solar systems, but unfortunately you crash landed on a planet. At this planet, the sun is not round like our sun. It's shaped like the letters XX. And you have one hope, and that is that you brought this special Nonimaginum rod, as we chose to call it. It's this green thing in the center here. And if you're able to send the light from this XX sun onto that rod, it is magical and it can fix your spaceship and you can find your way back home. So the question then is just how do we design these optics to send the light onto this rod? And here also we attempted to attendue match it, so it should be possible. It turns out that it was actually not a perfect attendue match. It was actually a little bit easier because there was less attendue on the source than on the target. But despite that, it's not that easy to find the right solution. So the challenge was getting the highest possible efficiency. And I will briefly tell you who the winner was. It was Ludo Heinen from Signify, and he presented a design of 53.3% efficiency. It's not so easy to see here what he did, but let's do a section view. And we can see that the first thing he did was he sort of imaged this source. And that brings up this interesting point because non-imaging optics, it's not about being against imaging or like avoiding imaging at all costs. It's just that our goal is not imaging. Our goal is to transfer energy, but imaging is often a useful tool for transferring energy, just not always. So he imaged the XX source, and then he created an aperture to let this image into a secondary concentrator. And in the secondary concentrator, if you view it from the top, it's sort of like an involute CPC looking design. Not exactly, it's optimized, but it looks somewhat like that. And this gave him the high efficiency. But I also want to show a couple of other interesting solutions. So this one was designed using light tools, commercial optical design software, but we had a few people submitting designs that they wrote code for themselves as well. We had Alex Lehmann, who made a design in MATLAB, and this was actually the best design among the participants at the conference, so he received a prize as well for this design. And then we had Jean-Baptiste Keck and Victor Pugon, who both did their own ray tracer in Python using a Python library called PyTorch. So Jean-Baptiste, he did it custom for this competition. And Victor Pugon, he has actually developed his own ray tracer based on PyTorch, which is a little bit more general, but then he applied it to this design competition. And PyTorch, that's like a library for making AI models, like machine learning library. So it might be surprising that you can use that to design optics, but it actually fits very well. And to be clear, this is not using AI to design the optics. This is using the tool that we use to build AI to instead build optics. It makes it possible to optimize freeform systems with way more degrees of freedom than conventional methods. And I find it quite interesting. So I'd love to chat with any of you afterwards if you're interested in this concept. I also want to briefly show another interesting submission that we had from John Huggelin. He used CMX Optics Studio, and he also did a primary that partially images this XX-shaped sun. And then he did this light pipe thing and put the receiver inside the light pipe to get light onto it from both sides. In total, we got these submissions. If you want to read more details, we have a proceedings paper about it. And Tom also did a full presentation about this competition, which has been recorded and is available on SPIE Digital Library. But now let's move on to this year. So as I said, our challenge is to fit the light from a square peg through a round hole. And the story is as follows. You receive this kind of strange item, and you're trying to figure out what it is. It looks like a children's toy where you're supposed to put like the correct shape into the correct hole, but you didn't get any shape that fit any of the holes. You just got this square cube looking thing. And this cube has this very strange emission profile. So you bring this into your lab to try to figure it out. And in your lab, you can sort of view the rays of the light coming out of this cube. And you see that they're like all very parallel to each of the 6 surfaces of the cube. So you bring out your calculator, you calculate the attendue, and you realize that it's perfectly matched to a disc shaped exactly like the hole in the center of this toy. So it turns out that this strange item that you received, that's actually a design challenge. Luckily, you have a 3D printer that can print perfectly specular optics. So the challenge now is how do you design these optics to take all the light coming from this source and redirect it onto this disk on this green target. So to show you a little bit more about the source, it has side length 45 millimeters, and it emits uniformly spatially, but in angular dimension, it has a constant luminance at high angles, but 0 luminance at angles of 66.3 degrees or lower to the surface normal of each face. If we instead plot the luminous intensity, we can see that this is exactly like a Lambertian surface, except that we have blocked the central region of emission. So it just emits like sideways and not to the center. The target is just a flat disk, diameter 50 millimeters. So any light that enters this top hole of this toy, we consider successfully delivered. And the goal now is to get as much as possible of the light through or into this disk. We have a build volume of our 3D printer of 500 by 500 by 500 millimeters, only reflective optics, no lenses. Light leaving the build volume is considered lost. The source is perfectly absorbing. So if you send light back to the source, it's lost. And you can move the source around, but you need to keep it a little bit away from the edge. And the target is at the bottom of your build volume. You can use STL or step files, but you have a maximum file size of 100 megabytes, and mirrors are 95% reflective. So that's a brief summary of the rules. You can see it in details on our website. But I think I want to do a live demo because I want to show you how you actually participate in this competition. So now I will bring up our website. And I go to the Optical Design Competition, and I first read the full description here. So we have the description, full rules, etc. And then I just go ahead and say upload my design. And here we have our lab, and we can try different designs. Right now we are at 0% efficiency. And to get you started, I thought let's try something together. Like a first thought might be that we try an ellipse, because if we take an ellipse and take one focal point at the source and one focal point at the target, that should get us somewhere around this. Yeah, get us somewhere at least. So now I just loaded an ellipse step file that I made in just some CAD software. Right now we're at just 1% efficiency, but that's because the source is not yet at the focal point of the ellipse. And this ellipse actually has a focal point at 150 millimeter from the bottom. So if I do that, we can see that the efficiency is still quite low. Let me zoom in here. And we see that most of the light misses the target still. And that's because an ellipse is perfect for a point source, but this is so far away from a point source that it doesn't really work. But we have something that's slightly closer to a point source, and that's one of the surfaces. So if I just move this cube a little bit up, so I align one of the surfaces with the focal point of the ellipse, so I move it to, what is it then, 172.5 millimeters, then I get approximately 17% efficiency. This is a rough estimate. I can press perform ray trace to do a more accurate simulation. This is ray tracing in JavaScript. It's not super fast, so we need to be a little bit patient. But if we wait a little bit, we will get a better estimate of the performance of our initial test. And this is now simulating, and it's almost done. And we got 14.8% final efficiency. But that's enough to prove that we can fit at least part of the light from a square peg in a round hole. So it's good enough to submit. So I can just continue to submission. And I've already signed in now. If I had not, it would ask for my email address to sign in. And it asks me to explain what I did. So I can say that ellipse placing one face at the focal point. And it asked me if I plan to attend the conference. And yes, I plan to attend. You're fully welcome to participate if you're not going to go to the conference, but we will have a special prize if you're coming. And I can enroll my design. It has been successfully enrolled. And now I have my submissions here, and I have this one submission. And if I am now thinking, oh, I have another idea, I just go back, build and upload something else. I can try as many times as I like. And the best submission is what counts. But we might also actually, if you submit something interesting, we can also highlight that even if it's not your best submissions, because we will look at all of them. So that was a live demo, and that was also the end of my presentation. And we are just at the end of the time. So I think we will go towards an end of this Nonimaging Optics Minisymposium now. I want to thank everyone for joining this Nonimaging Optics Minisymposium. And I want to remind us all about what Tom showed us in the start. We are meeting again in August in San Diego, and our call for papers is open on our website. So please think about something that you would like to present, and you're very welcome to submit an abstract. And I hope to see as many as possible of you in San Diego in August. And also, I hope that you have some ideas. I'm really curious to look forward to or to look at the submissions for the design competition. Last year, it was really lots of creative submissions, and I'm looking forward to the same this year as well. So with that, I will close this webinar. So thank you everyone for joining.
Thanks. Bye.
Bye-bye.